Miss Heaton signing in to talk with you about rate law expressions. Today we're going to be mathematically describing the overall rate of a reaction. Previously in this unit we've looked at how reaction rate can be sped up, specifically explained by collision theory. Now we're going to be looking at mathematically describing how the concentration of the reactants changes over a period of time, and writing an equation or an expression for that. So our first example is going to be looking at this reaction here. 1A reacts with 3 B's to make 1AB3. This is just kind of a generic reaction, similar to anything that you might encounter. And what we're going to do is describe the rate of this reaction. Now, let's think about this. What factors are going to affect the rate of reaction? Well, we've talked about 5, but the one we want to hone in on today is concentration. Now, does the concentration of all the chemicals matter? Well, no, because collision theory says only the reactants have to collide with each other. So the only thing we're going to care about in terms of writing our rate law expression are the reactants. The product does not matter at all. So let's consider this reaction. Let me show you what the generic equation might look like for the rate law. It's going to be something like the rate is going to equal the constant times the concentration of A to the M order times the concentration of B to the N order, or exponent. The units on rate are always going to be molarity per second because we're looking at how molarity changes over time. The units on K are going to vary, but they're going to be whatever units and whatever number it needs to be to make the ratio kind of work out. A and B in brackets represent the concentration or molarity of each reactant. Now it's possible that you could have a third reactant. What if there is reactant C here? Well, then we'd have C to the P power. Notice that we go M and P. We skip O because it looks like a 0. And now let's talk about what that M and N mean. Those are the order of the reaction. So they kind of tell you how strongly the concentration of that chemical affects the speed of, or the rate of, the reaction. And the order is going to be some integer. So it'll be 0, 1, 2, 3, 4. I don't know that I've seen anything go higher than 4. Now, one really important thing to notice is that these orders, or exponents, are not going to be the same as the coefficient from the reaction. Just because there's a 3 in front of the B does not mean that N is 3. In fact, those coefficients aren't going to matter because of mechanisms. The reaction may not occur exactly where 1A collides with 3 B's. We're going to look at that in a later lesson. So, experimentally, we have to determine this data. We can't look at the balance equation to figure out what the order is. We have to do experiments. Now, you can't do the experiment at home. I can't do it for you in the screencast, although we will get a chance to do it later in the lab. So today I'm going to give you some data. And there should be a PowerPoint file posted on the website where you can get these experimental data sets. Otherwise, you need to write them down. You cannot just write down the work here because you aren't going to be able to follow your example in class. You have to have the data accessible. So if you haven't yet printed off that data or written it down, please pause and do that right now. Okay, so what we've done are 3 different experiments, and in each experiment we have changed the amount of one of our reactants, or the concentration of our reactants, and seen how the rate is affected. And what our goal is to figure out the rate law expression, or that generic equation with filled in numbers for this particular reaction at this particular temperature, whatever temperature it was done at. So what we see is that in experiment 1 we used 0.1 molar of A and 0.05 molar of B, and the rate was this number. It's a pretty small number, so it's a small change in concentration over time. Then we kept A the same in experiment 2, but changed B and saw that the rate was a little bit faster. And then in experiment 3 we used a lot more A and the same amount of B, and the rate increased a lot. So what we want to do is fill in our generic rate law equation, rate equals K times A to the M times B to the N. We want to fill in values for K, the constant, M, the order on A, and N, the order on B. What we're going to do first is figure out each of the orders. And in order to do that, get it? In order to do that, we are going to compare 2 experiments where only A is changing and B is constant. Just like in any experiment, you want to control all the variables except the one you're looking at. So we want to pick 2 trials where the amount of A is different and see how the rate is affected by that difference. Because in experiments 2 and 3, A is, between those experiments we use twice the amount of A, so let's see how the rate is affected by that. And we can assume, or we can notice that B is constant, which will make our calculations a little bit easier. So what we want to do is compare the rate of reaction 3 to the rate of reaction 2. And I like to list my larger rate or my faster rate first, only because that's going to make the math a little bit easier. It will give us some nice integers. So what we'll do is write out the generic rate expression with each of the values plugged in for experiment 3 and then for experiment 2. So rate equals K, which we don't know yet, times the concentration of A in experiment 2, that was 0.2, to the M power, we don't know that yet, and then the concentration of B was 0.01 to the N power. Okay, and then for reaction 2, the rate was 2.7 times 10 to the negative 7th. That equals K times, let's see, A was 0.1 to the M, and B was 0.01 molarity to the N. Now what we'll do is compare those two trials, kind of setting up a ratio. One thing that you'll notice is that by picking two trials where B was the same, concentration-wise, is that those cancel out. Just like in math, if you have something in the numerator and denominator, it will cancel out. So this will now simplify to something that we can solve algebraically. So we can divide these two numbers by each other, and when you do that, you get the number 4. And over here we have 0.2 over 0.1. Now these are both to the m power, so what we can do is take that exponent outside both of them, so 0.2 over 0.1 to the m, which is basically 2 to the m. So what we see is that when we doubled the amount of A, the rate quadrupled. So we can kind of use process of guess and check to figure out what the value of m is, and we know that 2 to the second power is 4. So that means that the exponent on A, on chemical A, is 2. We can do the same thing to figure out the exponent on B. And we don't have to go through all of that every single time. I know you're breathing a sigh of relief there now, right? Because that was a lot of work. What we can do is just find two trials where A is the same, where B is different, and see how the rate is affected. And since last time K and the chemical that was constant canceled out, what we can do now is just write the rates in and that concentration of the chemical that changed. So we're going to compare the rate of reaction 2 to the rate of reaction 1. So the rate for 2 was 2.7 times 10 to the negative 7th. The rate for 1 was 1.35 times 10 to the negative 7th. And that's going to equal, let's see, in experiment 2 we had 0.01 of B, and in experiment 1 we had 0.005 of B. So those are both to the n power. Whoops, not m. N. And so we see that we have 0.01 divided by 0.05, that's 2. So 2 to the n power is what? And when we divide these two numbers, we see we also get 2. So when we double the amount of B, the rate doubled. So it means that's a first order dependence. So n will be 1. Okay, we're halfway there. We're 2/3 of the way there. We have found the orders for A and for B. Now our goal is to find K. So let's get this cleared off. What we have here is a summary of what I had up here in the corner earlier. Oh, one thing before we go on. I may ask you occasionally to find the overall order of the reaction. That just means the sum of the exponents. So it'll be 2 plus 1, or third order overall. Okay. Now I will often ask you, or almost always ask you, to find K, the rate constant. This is really easy. All you need to do is pick one of the experiments, doesn't matter which one. I always pick experiment 1 because it's easy. And just plug in all of the experimental values where they go in the rate law equation and solve for K. So if we plug in values from experiment 1, we will see that the rate is 1.35 times 10 to the negative 7th. That equals K, which we don't know, times 0.1 to the second, times B, which is 0.005 to the first. And then you just kind of multiply that out, and you get that the product of these two numbers on the right is 5 times 10 to the negative 5th. That equals 1.35 times 10 to the negative 7th. Then to get K by itself, divide both sides by 5 times 10 to the negative 5th. So it looks like our rate constant at this temperature for this reaction turns out to be 0.0027. Now, we don't like negative numbers. Every number needs to have a unit. And so what we want to do is pick units for K that will make all the other units cancel out. So let's go back to our equation here and rewrite it, replacing all of the numbers and variables with just the units on those numbers. On the rate, the units are molarity per second. That equals K, which we're trying to find the units for, times A. It's in brackets, so that means that it's a molarity, and that's squared. And the molarity of B will just be to the first power. I'm going to switch colors here so this doesn't kind of bleed into the work we did over here. So what we see now is that we have molarity per second equals K times molarity to the third. Now we want the units on K to be something that will cancel out molarity and end up with per second. So mathematically we'll divide both sides by m to the third. That's a 3. So molarity here will cancel out with 2 of these. Or sorry, with 1 leaving 2. So molarity squared. So then the units on K are 1 over m squared, molarity squared second. 1 over molarity squared second. You're probably thinking, oh my gosh, that's a lot of work. I don't want to do that every time. Don't worry, stay tuned. I'm going to show you a shortcut for that in just a moment. But before we go on, let's put it all together. So the rate law expression for this reaction would be rate equals K, which we just found the value of, 0.0027, and the units are 1 over m squared seconds, times A, this concentration to the second, times B's concentration to the first. And the usefulness of this is that based on our experimental data, we can predict what would the rate be at any combination of A's concentration and B's concentration. Your teacher may prefer you to keep the K values separate and just write K in the expression. Talk to your teacher to see what they prefer. Okay, let's kind of summarize all the steps that I just taught you. Here are the steps to finding the rate law expression. First off, write the generic rate law equation. And as I showed, include all of the reactants. If there's only one reactant, you just have A to the M. If there's others, include those. Then compare 2 trials at a time where one reactant changes and all the other reactants don't. In the advanced screencast, you'll see an example of one where you can't do this and what you have to do. Essentially, it's just plugging in numbers like we did for that very first example that I did. Number 3, calculate the value of K by plugging in values from any of the 1 trials. And as promised, here's your favorite part, the shortcut for finding the units on K. The units on K are always going to be 1 over molarity to the overall order minus 1. So in our last example, the overall order was 3 because the exponents added up to that. So 3 minus 1 times seconds. So that turns out to be 1 over m squared seconds, which is what we found doing all the algebra. And then finally, check your answers by plugging in numbers from any one trial. Oops, I didn't show you that. You should always check your answers. Okay, what I'd like you to do right now is hit the pause button, try to determine the rate law for this reaction, and once you think you got it, tune back in. Welcome back. Here's the answer to the example problem number 2. The rate expression is rate equals K times NO's concentration to the second, and K's, the value is 1.2 times 10 to the negative 6th, 1 over molarity seconds. Now, if you need a little bit of explanation, stay tuned. If not, you are done for now. Let me go through kind of what we did here. So first you start off with the generic equation. The difference between our last one is that we have actual chemicals this time, so you should always use those actual chemicals, NO and O2, in your rate law expression. Then to find M, we compared experiments 1 and 3. The concentration of NO tripled, and as a result, the rate increased 9-fold. This is where people often make a mistake. 3 to what power gives you 9? Well, that would be squared, 2. It's not third. 3 to the third is 27. For n, to find the exponent on O2, to figure out how O2 affects the rate, you'd look at experiments 1 and 2. There the concentration of O2 doubled, and the rate does not change. So plugging that in mathematically, you'd see that the rates are equal to each other, so it's a ratio of 1. And the concentration of O2 has doubled. So 2 to what power gives you 1? Remember from math that anything to the 0 power gives you 1. So that would be an example of a 0 order reaction, meaning that that chemical actually does not affect the rate. And in the mechanism screencast, you'll see why that might occur. So plugging that in, your rate law expression would just be rate equals K times NO squared. You don't have to include the 0 order O2. Then solving for K, I used experiment 1, mathematically manipulated it, and got 1.2 times 10 to the negative 6th. To get the units on K, it's going to be 1 over molarity to the overall order, which in this case was just 2, minus 1, which is 1 seconds. So it's 1 over molarity squared seconds. Okay, stay tuned for the advanced screencast if you're feeling ready for it.